So we've got about 15 minutes left for today. I want to just kind of dip into a little bit of chapter 5, because what we will find is that chapter 5 basically takes those drawings that we were making at the end of chapter 4 and starts to turn them into three-dimensional kinds of shapes. And so what we need to kind of process and go through in this chapter is transitioning from a two-dimensional piece of paper to describe a molecule to trying to think about things and visualize it in 3 dimensions. And so we're going to start this chapter kind of where we ended the last one. Looking again at nitrogen dioxide. And again, recognizing this has a resonance structure, we're just not going to draw it in here. Based on what we know as of right now, how many of those questions at the bottom can we answer? Can we determine the polarity of the bonds in nitrogen dioxide? Absolutely. Remember, that's what electronegativity difference was all about. I can look at the electronegativity of nitrogen, compare it to the electronegativity of oxygen, subtract them from each other, and determine if that is a polar bond or a non-polar bond. Polarity of bonding is something that we can establish if we know the 2 atoms that make up the bond. But the other 2 questions we can't answer at this point in time. And if we tried, we probably wouldn't answer them correctly. After all, I look at this particular molecule the way I draw it, and I would say, okay, yeah, it's easy. The bonds are 180 degrees apart. They form a line. According to the drawing, absolutely correct. According to reality, no way. Those bonds are actually less than 120 degrees apart. Is this a polar molecule? Again, I have no way of knowing that just by looking at it. I could look at this and say, okay, well, I've got a polar bond going this way. I've got a polar bond going this way. The 2 polar bonds are the same, nitrogen to oxygen. Looks like they maybe cancel out. Reality, this is a polar molecule. It will dissolve in water. So as good and useful as Lewis structures are for helping us to figure out how a molecule is put together, we can recognize that there are some places where it doesn't do a great job of explaining all of the properties and characteristics of the molecule itself. It tells us what kinds of bonds are there, but it doesn't necessarily tell us all that much about the molecule itself. So we need more. And the more that we need is we need a better model. We need a better way of expressing how those molecules are put together and how they arrange themselves in 3-dimensional space. The model that we're looking for, the model that we're going to use, is something called the valence shell electron pair repulsion theory. I'll say it again. The valence shell electron pair repulsion theory. Now, I said it those 2 times because that is the only 2 times I'm actually going to refer to this particular theory by that name. From henceforth, we will call that VSEPR. And VSEPR theory is the theory that we are going to use to help us to answer some of those other questions. What VSEPR does is this. it is going to help predict how those valence shell electrons, the ones that are responsible for bonding, arrange themselves in three-dimensional space. And they're going to do so in a way that minimizes repulsion. After all, we're talking about electrons here. Electrons are negatively charged. Negative charges repel each other. So there's a limitation to how close we can get all of those electrons to each other without the whole thing flying apart. VSEPR theory gives us a means of trying to explain how they arrange themselves. And the net result of that theory are shapes. There are going to be some set shapes that come out of this theory that help us to predict how a molecule is going to look in three-dimensional space, how an ion is going to look in three-dimensional space. And with that in mind and with that in play, we're going to be able to do more to talk about some of those other questions. We're going to be able to talk about orientation. We're going to be able to talk about polarity of the molecule itself. We're going to be able to talk about how we actually can build and construct that molecule in the first place, because we're kind of glossing over some details right now. But we're going to eventually have to address them. This is going to help. To use the theory, we have to establish a couple of key terms. So you'll hear the term either electron pair geometry or domain geometry used in this unit. What that is referring to is the three-dimensional arrangement of the molecule, assuming all of the electron groups are the same, meaning they all have the same amount of repulsion, they all have the same amount of, for lack of a better term, weight. Now, reality is that on that center atom, which is where we're going to spend most of our time focusing, on that center atom, if there are bonding pairs versus unbonded lone pairs of electrons, those unbonded pairs are actually going to have a bigger impact on the shape than the bonding pairs will. But for electron domain geometry, we're treating them all as the same. That is going to be different from the actual molecular shape of the molecule. That's where we start to factor in the difference between unbonded electrons and bonded electrons. Because the bonded electrons, because they're shared between multiple atoms, don't have nearly as much repelling power as unpaired or unshared electrons that are just for that center atom and for nobody else. The reason we need to know both is because the molecular shape is fed out of that domain shape. If I don't know the domain shape, I can't know the electron, I can't know the molecular shape. So I have to establish domain geometry first. And this comes later. Some more terms for us to know. Again, in this chapter, we are going to spend the majority of our time focusing on the center atom, because the center atom is going to be kind of the middle, the hub that helps to establish the shape overall. So when we talk about bond angles, what we are talking about is what is the angle in degrees from one bonded area to another going through that center atom. So notice in both of these cases, we're not thinking about the bond angle from the center out to one of the atoms, because that obviously would be 180 degrees. The angle between any 2 points on a line is 180 degrees. What we're talking about is if I were to try to connect one atom on the outside to another atom on the outside, how far apart are they in degrees? One last piece of nomenclature of terminology here, at least at the beginning. Steric number. Steric number represents the total number of electron groups around an atom. Again, we're focusing mainly on the center atom in this case, but technically speaking, we could do this for any atom. But again, since center atom is really what determines the shape of the molecule, we focus on the center atom. For steric number, we need to look at the number of atoms that we are bonded to. So how many directions do those electrons go out from the atom? And so that's going to come in the form of bonding and unshared pairs of electrons around that atom. So let's come back to this nitrogen dioxide example. For the nitrogen, our center atom, our steric number is going to be 3. Now, how did I come up with 3? Well, again, how many directions are the electrons going? Well, I can count one direction here, a second direction there, and then a third direction for that unshared electron on the top of it. So when we look at bonding groups, we don't look at the number of bonds. So this is different than formal charge. Formal charge, we cared about the number of bonds. Here we care about the number of directions. So it doesn't matter if I have a single, double, or triple bond. If all of those electrons are going in one direction toward one atom, it counts as one center. So in this case, there are only 3 directions. One to the oxygen on the left, one to the oxygen on the right, and one to the unshared electron that's just kind of hanging out on top of the nitrogen there.
And if there was one on the bottom,
well, if there was another one, it would have been paired with the unpaired electron there. But if there were two sets of dots on the nitrogen, yes, it would be 4. Why we care about steric number is because steric number is going to help us predict shapes. Steric number drives our electron domain geometries. And as we know, the electron domain geometries drive the shape itself. So it kind of hinges back to this idea. If we can establish a steric number, we can start to establish its 3-dimensionality. And so that's where we will stop for today. On Friday, we're taking our exam. So we're going to put this away until Monday. On Monday, we will start to look at the actual shapes themselves. And then we will do some examples where we take actual molecules and start to try to put them into those categories. And that'll get us off and running into chapter 5 here. Have a good day. Hope to see you at the review this afternoon.